continuing with section 3.10, and this is related rates. This time, example number 6, Joe, who's 6 feet tall, is walking away from a 14 feet tall lamppost at a constant rate of 3 feet per second when Joe is 10 feet from the lamppost. How fast is the length of Joe's shadow changing? How fast is the tip of the shadow moving away from the lamppost? Let's remember this. Rays of light are straight lines, and light kind of emits straight lines, or we can imagine that the rays of light above somebody's head is going to go in a straight line. And so when let's say Joe's standing over there, the light from the lamppost, here's the 15 feet tall lamppost, the light from the lamppost goes above his head and then down here, but it doesn't go through him, so the shadow is built over here basically. And so we want to, the interesting part, the other interesting part is that we know that this shadow basically gets bigger and bigger as Joe moves away from the lamppost. And so also the distance when Joe moves away from the lamppost, the distance of Joe and the lamppost increases. So that's the beginning part of this, like introduction part of this question, that we saw that the shadow is getting bigger and bigger as he's moving away, and the distance is increasing. So let's call the length of the shadow S, and then the length of the distance from Joe to the lamppost, D. How are these related? Like lamppost is kind of a straight up lamppost, so it's making a 90-degree angle with the ground. So is Joe, and so basically you can see two triangles in here. One is this one, and then the other is this one. And because Joe and lamppost are both perpendicular to the ground, they're parallel to each other. According to what we learned in geometry, when you have another triangle, and there are two triangles that are sitting like this, and here they're sharing this angle, and they are both have a right angle. That means that all three angles of the two triangles are congruent, and therefore the two triangles are similar triangles. And so we have to use the fact that they're similar triangles to figure out how the S and then 14 and 6 and D are related together. So let's write down use the similarity to write down a relationship between S, D, 6 feet and 14 feet. In here, S, the ratio of S over 6 feet is the same as this side to 14 feet. What is this side? This side is S plus D. So I'm writing S over 6 is equal to S plus D over 14. And then I can simplify this a little bit, and I can write this as let's multiply both sides by 14, and then I get 7S over 3 is equal to S plus D. Right? I can also multiply by 3 and get 7s is equal to 3s plus 3d. Now, from here I get 4s is equal to 3d, or s over d is equal to 3/4. Now I can use this equation that connects, again, we discussed that s and d are both changing, and now I connected the two quantities together. Let's see which one I know at the instant and which one I don't know at the instant. As I'm reading, it says he's walking away from the lamppost at the constant rate of 3 feet. That means d is increasing at 3 feet. So I know that d over dt is equal to 3 feet per second. And now, now that I have this equation, I can take the implicit differentiation of this equation and get 4 is the constant, derivative of s with respect to t is equal to 3 is the constant, derivative of d with respect to t. I know this one is equal to 3, and then I can calculate ds over dt, and ds over dt is going to be 9 over 4, or 2.25 feet per second. So I answered the first part of the question. Now let's come back and answer the second part of the question. So in the first part of the question, we figured out that ds over dt, we calculated that ds over dt is 2.25 feet per second. And now, to find this distance is actually, we're trying to take the derivative of d plus s. According to the laws of the derivative, this is equal to dt dt plus ds ds dt, which is now if I figured out one of them, which is 2.25. This one is 2.25, and this one is this one was given, that was 3, so I can add them all up to get 5.25. And this makes sense. We're saying that and s is increasing at this rate, d is increasing at this rate. What is the rate of the increase of the two of them added together? We should just add the two rate of change. Example 7. A boat is pulled into a dock by a rope attached to the bow of the boat and passing through a pulley on the dock that is 1 meter higher than the bow. If the rope is pulled at the rate of 1 meter per second, how fast is the boat approaching the dock when it is 8 meters from the dock? Okay, so what is the entire story? We're discussing this distance of the boat, let's say from the pulley to down here, in that we call it d, and then we have the length of the rope r, and so what I did purposefully put the arrow that recognizes d in a position that d and that 1 meter and r are making a right triangle. And so basically from the bow of the boat to the pier, that's D, and then if you think about it, if you drop a perpendicular over here, and then the distance from the top to that base of that perpendicular has to be 1 meter long. And so what is going on as R is getting smaller and smaller, you see D is getting smaller and smaller too, and the angle that R makes with D gets bigger and bigger. Not that we are calculating the angle right now, but that's how it goes. Now, what are the knowledge that we have? The knowledge that we have is we know that this is 1 meter. We also know that rope is being pulled at 1 meter per second. So this is dr dt at the instant is it positive or negative? We just saw that it's decreasing, so it's -1 meter per second. And then we want to know how fast is boat approaching to the dock when it's 8 meters from the dock. So I know that at the instant D is equal to 8 meters. And so that's all the information that I have. And then I can set up the relationship between D and R, because I see that the rate for R is given and the rate for D is wanted. So again, there are a few things that usually happens with the triangles. You can have when you're trying to set up a relationship between sides, you can use trig functions. You've seen one example of that. You can make triangles that are similar triangles, and another option is when the triangles make you can use the Pythagorean theorem, and you've seen that one before also, but let's this is a slightly different type and we go over it. And so how do we relate all these? Is going to be 1 to power 2 plus D to power 2. D is changing, is equal to R to power 2. And when I take the derivative, 1 to power 2 is just 1, it's going to be 0. And then here 2D, again D is the function of T, and it's the outer function is x squared, inner function is D, and 2R dr dt. And the 2's from both sides are going to be simplified. What is remaining is, I know this is 8, I know that is -1, and if I knew R, I can find this, which is what question is asking. And so how do I figure out R? Oh, incidentally, at the instant that we're measuring all these, D is 8, and this distance from the top of the pier to this base is 1. So I can use Pythagorean theorem to find that, and that gives me square root of 1 plus 64. 8 to power 2 is 64. And then I can calculate the dr dt from there. Then dr dt is going to be a negative ratio because it's decreasing, and it would be, oh, I'm sorry, dt is going to be, that's the one with the question mark, is going to be a negative value, negative square root of 65 divided by 8, which is approximately, this is going to be equal to -1.008 meters per second. Example number 8. At a certain moment, ship A is 6 miles south and 8 miles west of ship B. ship A at that moment is steaming east at 12 miles per hour, while ship B is steaming north at 15 miles per hour. Are the ships approaching each other or separating from each other, and at what rate? And so let's draw a picture for ourselves. So ship A is and is basically 8 miles. We're saying ship A is 8 miles west of ship B, and this is 8 miles. And at that instant, and 6 miles south, and at the instant this is 6 miles. And so you're kind of getting the gist of this, because you see that there is another triangle, right triangle over here. And so we're asking, we know that these distances are changing, and we know some of the rates of change. Over here we know about that 15 miles per hour going north, so that the distance over here, whatever that is, and I can make that, call that B, is changing, but at that instant it's 6. Over here this distance is changing too, because the ship A is going east at 12 miles per hour, and let's call this one A. Now, we can call them X and Y. In this problem, we call them X and Y. Now, how do we relate this? And then this is the distance we're interested in. And so, as we see in the Pythagorean theorem, d squared is equal to x squared plus y squared. Take the derivative, and you will see this. And that's, again, implicit differentiation, x, y, and d. They're all functions of t, function of time, and then you plug it in. Again, in here, a bunch of things are given. At that instant, this is equal to 8, and this is equal to negative 12, because it's the x is decreasing. Y is equal to 6, and dy dt is equal to 15, and it's increasing, so it's a positive value. And then I don't know d, and I want to know dt, dt. And d is an easy computation by Pythagorean theorem, and I can see easily this is equal to 10. And so this is how we have to simplify and evaluate this dd dt, which dd dt is going to be negative 3 over 5 miles per